Welcome to the physics class for March the 2nd. I am not planning to go over the homework, seeing as how those of you that are in the A-Day class, I did not assign any homework last time. All you had to do was just the quiz. And if you were in the B-Day class, then that was a little separate. But if you're in the B-Day class, hopefully you watched the video that I posted and that I specifically said, watch this video, and that's where I go over the homework. So not planning to do that today. Today, I'm just going to jump right into the new stuff, which we are going to actually go back to chapter 16 now. I like to do things a little bit different order than the way that the book does. I think it's important that we talk about interference before we go back and do the other stuff. So yeah, a little out of order, but I think it flows better that way. Now, there is some more stuff in chapter 19 that we could do. If you look in the book, you'll see the very last part of the chapter there contains some really good stuff that I wish we could do, but hey, there's just not enough time in the year to do it all. Hang on a sec, let me let that late arriving student in. Okay, so now, but before we go back in chapter 16, I want to do a quick review of some important concepts because it will help you better understand the new stuff that we're going to go into. So up until now, we have seen two different examples where light does weird things because it's a wave, things that it would not do if it was a particle. Let me open up a whiteboard here and just draw a picture so I can summarize this really quick. So one of the things that light does, because it's a wave and not a particle, is the double slit experiment, the double slit effect. Okay, so here are two windows. Okay, here's the wall. Now, I should explain that you don't always see the double slit effect. It depends on how big the window is. If the window is large, so like if it's the window right here in your room, light comes in the window, what happens is the light goes right straight through. And so you get a bright spot right here, and you get a bright spot right here, exactly the same as if light was made of particles. So this is one of the reasons why Isaac Newton was convinced the light was made of particles, not waves, right? But if that opening is not large, if that opening is small, then that changes everything. Then instead of getting bright spots in the places where Isaac Newton thought that there should have been bright spots, what happens is you get a bright spot right here in the region that should be shadowed. That's where you get a bright spot. Okay. And then the region right here where it should, quote unquote, should be bright, it's dark there. And if you come over here, so then there's another bright spot up here and one on the other side. And if you keep on going, there's another bright spot up there and another bright spot down here, right? Cannot possibly be explained by the particle theory of light. Only the wave theory of light can explain it. And hopefully you guys are really good at understanding that now. So if this opening is small, then you get lots of diffraction, which means that the light rays spread out. And this one spreads out. Okay, so you got one light ray coming from here, the other light ray coming from here. They both travel the same distance. That means when the one light ray combines together with the other light ray, they will be exactly in phase, and they will interfere constructively. If you're up here, then hang on a sec while I get rid of those. Okay. All right, so then what you've got a light ray coming from here and a light ray coming from here. And this lower light ray had to travel a little extra distance. And so that lower light ray got shifted a little bit. And so it's out of phase, which means it interferes destructively. And so it's dark there. Now, if you shift it enough, then you get to the point right here. Okay, so now that extra distance that this lower light ray had to travel is now exactly one wavelength. So you get the one light ray, and then the other light ray has been shifted. So instead of starting over here, it starts over here. And so if that shift distance is exactly one wavelength, then they're going to be in phase. Even though one of them is shifted, they're still going to be in phase. And so they're going to interfere constructively. And so you're going to get a bright spot, and so forth and so on. So this proves that light is a wave and not a particle. And then the thin film interference effect is the same kind of a thing. Okay, that would only happen if light was a wave. So if you got, here's your thin film, you got a light ray coming along here. So part of it gets reflected and part of it gets transmitted. So it comes to here, again, part of it gets transmitted, some of it gets reflected. So when these two guys combine, if this shift distance and if the phase inversion works out such that these two are in phase with each other, then they'll interfere constructively and you'll see a bright spot. If the shift works out to where these guys are exactly out of phase, then you'll see a dark region. And so again, this is a phenomenon that can only be explained by the wave nature of light. All right. So I would like you guys to type in the chat box now. I want you to type in the word yes if you are now convinced that light is absolutely a wave and not a particle. And I'd like you to type in something else if you suspect that maybe there's still some little bit of craziness going on that I haven't yet told you about. Okay, so type into the chat box. Yes means yes, you're convinced light is a wave and not a particle. And if you want to type in something else because you're not quite convinced, then that's okay too. Come on, I need to see some things typed in here. Okay, I see a lot of you. In fact, so far, every single one of you is saying that you suspect that there's something else going on. Miriam says that she suspects it just because she knows me. She's been in the class long enough that she understands how my mind works. She knows that I wouldn't ask the question unless there was, in fact, something else going on. Okay. Gia is she's saying yes, but it could be both. So Gia, can you maybe unmute yourself and elaborate? I mean, why are you not convinced? What makes you suspect that there's something more going on?
I just said that because I know that there's still photons and particles of light involved with light, and I'm not really sure about that part.
Okay, how do you know that?
Just like from past science classes.
Okay. Okay. All right. So Gia recognizes that there is still something going on here that we haven't yet talked about. Everybody, well, a lot of students have heard that light is sometimes a wave and sometimes a particle, or maybe what they've heard is that it's a wave that has particle-like properties, or I've got a couple students that think that the reason that light travels through outer space is because what happens is when it's traveling through outer space, it converts itself into a particle. And it travels as a particle through the space. And then when it gets to the air, then it converts itself back to a wave again. So there's all sorts of really weird theories going on out there. Well, the truth is also quite weird. But yeah, so let's talk some more about that today. That's one thing that's one thing I think is really important. You understand that, yes, there is something more going on. And so let's find out what that is. The best way, I think, to explain it is for me to open up this Desmos graph. So this is the graph that we were talking about. We were using this when we were trying to understand thin film interference. And so remember, in fact, let me go ahead and turn on the picture here. All right. Okay, so this is a screenshot from the video when we had the soap bubble and we placed the soap bubble on its edge there. So if we were to look at it from a side view, so here's the upper hoop, here's the lower hoop. Up at the top there, it's really thin, and at the bottom, it's really thick. And the reason is because gravity is trying to pull the water down, but the soap bubble is fighting it. So as time goes on, you notice these rings, they move down and down and down. That's because water was slowly moving down. So the top part was getting thinner and thinner as time went on, and the bottom part was getting thicker and thicker as time went on. So in order to help everybody understand that, I used this this Desmos page right here. Now I only did it with one light wave then. I'm going to do it with 2 light waves now, but let's go back here and let's recreate what we did before. So what you're seeing is a light wave, and it's just a generic sine wave. You know, just this. Now I put in a +2 because I wanted to raise it up. Don't worry about the +2. So this is a generic sine wave, as simple as it can get. And then over now down here, this is another sine wave. And you can see I can shift them using this little slider here. All right, so the first wave, that's the wave that reflected off the front surface of the film. In fact, let me turn this back on again here. Let me turn on annotation again. All right, so here's the film. Okay, so we get one light ray that reflects off the first surface, that's R1, so that's this guy. And then the second light ray went through the film, bounced off the other side, came back, so that's R2. So R2 here. All right, now, hopefully you guys remember that R1 got inverted. So if I want to capture that in my graph here, what I'm going to have to do is I'm going to have to put a minus sign in front of there. So there's my minus sign. Okay, good. All right, and R2 did not get inverted. All right, so if the shift, well, now the shift can never really be exactly 0. So it's a number that's so close to 0 that it might as well be 0. Okay, so you see, we got R1 and R2 are exactly out of phase, or at least they're super close to being exactly out of phase. And so they are going to interfere destructively. And now let's look at this other color here. So if we do the same thing for this red, so I've got a blue light wave and I got a red light wave. And again, let's make the one that reflected off the first surface got inverted. Okay. All right. So you can see that both of the light waves, both the blue wave and the red wave, they both are interfering destructively, which explains why it is that we have black up at the top here. So red, green, blue, yellow, all the different colors, if the film thickness is so close to 0 that it might as well be 0, they are all interfering destructively, and that's why we see the black region down there. Now, let's see what happens as we move down in the film here, because we move, the further down we go, the thicker the film gets, right? So let's look and see what happens here. So we got the black region up here where everything's interfering destructively. As we move down, we get into a white region. It's not a perfectly clean white. It's a little bit of a dirty white, but it's mostly white. All right, let's see if we can understand why that is the case. So here's our waves. And let's increase the thickness a little bit. Okay, so if I bring it to right here, you can see that the blue wave is now fully constructively interfering. The red wave is a little bit off because, you know, it has a different wavelength, right? So it's not perfectly constructive, but it's pretty close. It's pretty close. And in fact, if I shift it just a tiny bit more, I get to a region here where look at what's happening here. The blue wave is not exactly perfectly constructive, but it's darn close. The red wave is not perfectly constructive, but it's also darn close. And so would the green and the yellow and the blue. So there is a region here where all of the colors, they're not exactly constructive, but they're close enough. So it's not surprising that we're going to see white, because remember, white is a combination of all the colors, right? Now, what happens as we keep on shifting? So we move further down in the film. So the shift continues. So let's keep shifting here. So now we get a point where the blue wave is now completely destructive. The red wave, not so much. I mean, kind of, sort of, but it's a little bit off. Let's keep on shifting. Let's go. So now we get, okay, now the blue wave is now completely constructive. But look at the red. The red is definitely not close to being constructive anymore. It's about halfway between being constructive and destructive. So what's going to happen is if the blue wave is being perfectly constructive, That means we're going to get a very strong blue signal back, and we're going to get a very, very weak red signal back. And so if you zoom in here, you see, sure enough, that's what happens. Look, see that first band there, that beautiful blue band right there? And so that's because the blue is constructive, and the other colors are now so far off from being constructive that they're not really doing much. So if I keep on shifting, now I get to a point where the red is now constructive and the blue is now destructive. And then the same thing is going to happen for the green and the yellow and whatnot. So what's going to happen is when we get down into this region right here, we get very beautiful, vivid blues and yellows and reds, and very bright and very vivid. Okay. Now, here's where it gets important. As we move further down, notice that the colors get muddier. You know, instead of having bright, vivid colors like we do up here, when we get down into here, notice that they get to be really red and really muddy. And also notice that the yellow and the blue start disappearing. So all we're seeing now are mainly just the red and the green. And in fact, if we go down even further, when we get down in here, even the green starts disappearing, and now we mostly just see red. So why is it that the colors which used to be so bright and vivid are now dull and muddy? And not only that, but they start disappearing. The blue one is the first one to disappear, and then the yellow one is the next one to disappear, and then the green one's the next one to disappear. Okay, so what's going on here? Why is that the case? Well, what's happening is that light is not the kind of wave that you see when you look up here. So let's take this back to 0 again. Okay, and in fact, tell you what, let's get rid of these. Let's just, okay, what you are seeing right here is not the whole picture. I mean, yes, light is a wave, but it's not this kind of a wave. This is what I call a classical wave. It's a wave that basically goes on forever and ever in both directions. Light doesn't do that. Now at the time, the scientists didn't realize that. It was only much later. It was like when Einstein came along that that scientists started to figure out what is actually happening. So what we now know is that light is not a classical wave like that. Light is a quantized wave like this. This is what a light wave actually looks like. This is a little bundle of energy. And in fact, we could call it a wave bundle, or if you want, you could call it a wave packet. I like to call it a wave burp. Okay, the official name is it's a photon. Okay, so light comes in little burps like this. And so the explanation for that is one that I think you've probably heard. I mean, pretty much all of you have either had chemistry or you're currently taking chemistry. And in your chemistry class, your teacher, Coach Miller, has told you that what a molecule looks like is, you've got the nucleus here. It's got all these, protons and neutrons in the nucleus. And then you got these little electrons that are buzzing around, on the outside here. And what happens is you can, like, if you look inside the sun and look what's happening in the sun, why is the sun giving off light? Or why does a flame give off light? Or why does a light bulb give off light? It's because what happens is that somehow one or more of these electrons gets bumped up to a higher level than it would normally be at. And there's a bunch of ways you can bump it up in energy. What you can do is you can heat it up thermally. That will cause it to jump up. Or you could zap it with electricity, or, there's a bunch of ways. So this electron wants to be here, but because we gave it bump of extra energy. It jumped up to this higher level and it absorbed energy when it did that. But it doesn't like being at that higher level. So what's going to happen is it's going to relax back down to the level where it likes to be. And when it relaxes, it gives off a burst of light. Okay, so that is what is happening inside of the sun or inside of a flame or inside of a light bulb. This is where the light is coming from. You've got all of these individual atoms, and each time an electron jumps from an excited state down to a lower state, it gives off a little burst of light, but it is an extremely short burst. It is most definitely not a continuous wave. Let me go back to Desmos here. Okay. It is not going to be a continuous burst like this, because the event that causes the light to be emitted is an extremely short event. It only happens for maybe a fraction of a second. So what you get is a very short duration wave. You get what's called a photon. So when you look out the window and you see light coming in the window, and you think that it's a continuous stream of light, it's not a continuous wave. I mean, it is a continuous stream, but it is not a continuous wave. It's not what you see up here. What it is instead is it's a whole bunch of little photons. So you're getting gazillions of photons, one after the other, after the other, after the other, but they are not necessarily in phase. So let me draw a picture here. All right, so here comes one photon, and it's followed by another photon, which was emitted at a slightly later time than the first one was. But this second photon and this first photon are completely unrelated. The phase of this guy and the phase of that guy are not at all the same. So it's not like you got this big, long, continuous wave. You got a whole bunch of these photons. They're all completely independent from each other. And so if you want to have thin film interference, let's say that you got here's your thin film. And so you've got a wave coming along, and some of it reflects there, and the rest of it goes through the film, hits the other side, comes back, reflects off here, some of it's transmitted. This part of the wave and this part of the wave, they are only going to be able to interfere with each other if they both come from the same photon. Because if you have one photon that comes along and it does this, and then another photon is coming along behind it, these two photons are completely unrelated to each other. They are not in phase. So one photon cannot interfere with another photon. A photon can only interfere with itself. Okay, so now let's go ahead and let's take a look at this shifting here. Whoops, I just got a message saying that my camera is off, but it's not showing me. That's odd. I don't understand that. So, oh, I see. Oh, look at that. Somehow my camera got shifted to the rear mode. How in the world did that happen? Okay, now how do I turn it back to being the forward camera here? That's really weird. How did that happen? Okay, so now we're back to the forward camera. Is it good now? You're seeing me? So when did that happen, Aurora? Is that just happened a minute ago? Or has that been going on the whole time?
I think it just like happened.
Okay, so, all right, so up until a brief time ago, you were seeing me. Okay, thanks for telling me that, Aurora, I appreciate it. Okay, so let's go back here to my coherence length demo. Okay, so let's explain why it is that the colors are bright and vivid up here, but as you get down here, they go muddy. All right, so I need two waves. So the first one here, this is the wave that got reflected off the first surface. This lower one, this is the wave that got reflected off the second surface. You see there are actually two waves, okay? But remember that the wave that got reflected off the first surface got inverted. So let me put a minus sign there. All right, so let's look at this photon now. right? So if the film is so thin that it's so close to zero that it might as well be zero, you can see that the shift is very, very small. And so you can see that the photon can easily undergo destructive interference. So what you're seeing is like this part of the wave is combining together with this part of the shifted wave, and they clearly are going to cancel each other out. So when you see this here, you're going to get destructive interference, which means that the top part of the film here is going to be black. Okay, and so now let's see what happens as we shift it further. So now I've shifted enough. So now you can see I'm getting constructive interference. Now the amplitudes are a little off. So here is this is the wave, the part of the wave that got reflected off the front surface. This is the part of the wave that went through the film, reflected off the far surface, and then came back. So you can see that the amplitudes are a little bit off, which was not the case before with the classical wave, but that's okay. They're still interfering constructively. So yeah, that makes sense. But now let's shift it some more. Let's see what happens if I shift it over here. So now this is where we should be getting destructive interference. In fact, if you look up here at the classical wave, let's do this classical wave here. With the classical wave, we absolutely have destructive interference. You see we got a peak up here lining up with a trough down there. Total destructive interference. Well, we still, down here with the photon, we have destructive interference, but it's no longer total destructive. Because if you look at this part of the wave right here, this is the part from the wave that got reflected off the front surface. And it's trying to combine together with this wave. This is the part of the wave that reflected off the rear surface. And you see that we've got a big amplitude here interfering with a small amplitude there. So yeah, they're interfering destructively, but it's not going to be total destructive interference. And in fact, it gets even worse and worse as we shift it further here. So let's shift the wave some more. Okay, so now we're back to constructive. Now we're back to destructive. And you can see that it's even worse now. The mismatch between the part above the line and the part below the line, it's even worse. And in fact, as we keep on shifting it, now we're back to constructive, now we're back to destructive. See, we're not going to get very good destructive interference at all now, because the part of the wave that reflected off the front surface, look how big that part is. And look how tiny now is the part that it's trying to interfere with. So it's not going to be able to interfere. All right. So that explains why it is that as you go deeper down here, as the film gets thicker and thicker and thicker, is that the photon, we've exceeded the distance that the second wave had to travel, went through the film, reflected off the other side, came back. That extra distance that the second wave traveled is now greater than the width of the photon. In fact, there's a term here that we need to learn. It's called coherence length. So if you look at a photon and you ask yourself, how long is a photon? Well, it's kind of hard to say, because if you look at the envelope goes to zero asymptotically. So it never completely reaches zero. But you do get down to a point where it's so close to zero that you really, might as well be zero, right? So exactly where we draw the line here is kind of fuzzy to define. It depends on how sensitive your instruments are. But this length right here is what we call the coherence length. And so if you've got some film here, so this is the light that reflected off the front surface, this is the light that reflected off the rear surface. So this distance here, 2 times t, that's, it went through the film. And so there's 1t, it came back. So the 2t is how far the second light ray had to travel that the first one did not. So if 2t is greater than the coherence length of the photon, then these two guys are not going to be able to interfere with each other, right? And so what you're going to see is that as the film gets thicker and thicker, you no longer see the thin film interference effect. And it fades out slowly. The first one to go is the blue. And then because the blue has the shortest wavelength and therefore the shortest coherence length. So as you start off at the top here, and you see here's a beautiful blue color, you get down in here, you don't see the beautiful blues anymore because you've exceeded the coherence length of the blue light. And same thing with the yellow. Up here, you see some beautiful yellow lights. But when you get down below a certain length here, you no longer see the yellows because the film thickness now exceeds the coherence length of a yellow photon. And so you get down in here and all you see are the reds and the greens. And as you get down even further, now all you see are the reds, because once you get down into here, you've now exceeded the coherence length of the green photons. And so the only photons that you have any hope of having any interference with now are now the red ones. And in fact, if you were to keep on going down, you get a point where even the red ones are no longer able to interfere because now you've exceeded the coherence length of the red photons. So this explains, here, let me go back to here again. So this is what you've heard about when people tell you that light is both a particle and a wave. This is what they mean. And they should not say that light is a particle. It is absolutely 100% wrong to say that light is a particle. It is a wave. It is absolutely 100% a wave. Always, always, always. It's just not a classical wave. It's a quantized wave. And so it comes in little bundles. And so I can understand why people are tempted to call it a particle, but you really shouldn't, because if you say that it's a particle, that leaves people with the impression that it's like a little ball that is traveling along. And that is absolutely not the case. It is not a particle in any way, shape, or form. It's just a quantized wave. Okay. So hopefully now you guys understand a little bit more about what the true nature of light is, okay, and why people say that it's kind of like a particle in some regards, even though it's absolutely still a wave. Okay, good. So give me thumbs if that makes sense. Thumbs up if what we said makes sense, and if not, then type in a question mark. Okay, good. I'm seeing lots of thumbs. All right, great. Now, what kind of a wave is it? Hopefully you guys remember the waves come in two varieties. There's transverse waves and there's longitudinal waves. So which one is this? If only there was some sort of a test that we could perform, some sort of an experiment that would answer the question of whether it's a transverse wave or a longitudinal wave. Now, actually, before we go into that, let me make sure that everybody remembers what we're talking about when we say transverse and longitudinal. Vian, would you mind unmuting yourself and just remind everybody, what does it mean for a wave to be transverse or longitudinal? What does that mean?
Transverse waves are the ones where the disturbances are perpendicular to the motion of the wave.
Excellent.
And then longitudinal are the ones that
that is parallel to the direction. Okay,
yeah.
very, very good. Yes, that's exactly right. Okay, so let me go into here. All right, so the great example of a transverse wave would be a wave on a string. All right, so imagine that you've got a string and you're shaking the string in the vertical direction. And so all of the pulses on the string go up and down vertically. Right? If you were to take a piece of cardboard and you were to cut a long slit in the cardboard, and then you orient the cardboard in such a way that it's vertical. So all these vertical pulses that go up and down and up and down, they can pass right through this cardboard just fine. But if you were to rotate the piece of cardboard, so now over here you can see we've got the slit is arranged horizontally. So along come these vertical pulses. they are trying to get through this cardboard, but when they hit the cardboard here, they can't get through because the slit is horizontal and the motion of the string is vertical. So by rotating this cardboard 90 degrees, if that stops the wave from getting through, that shows you that it is a transverse wave. Now, just to make sure everybody's clear on this, what if it was a longitudinal wave? So let's suppose that it's a wave like a slinky wave right here. And so remember that this is like what sound is. So if we were to take a slinky and we compress the slinky, and then we take our thumb away and let it go. So we're going to get a compression pulse that's going to travel along the slinky. And then maybe a little bit later, we're going to do another one. So this is the first compression pulse traveling along this way. This is the next compression pulse coming along in between. And notice that in between these two regions of high pressure, there's a region of low pressure here. So this is exactly what a sound wave is. So imagine we've got imagine we've got a longitudinal wave like this. If we were to do the same thing that we did on the previous page here, so let's go back to the previous page. So what we do is we take that cardboard and we cut a slit in it, right? So if we were to take that and do that same experiment, so imagine here's the long skinny slit, and this is our piece of cardboard right here. Okay. All right, so this is the cardboard like that. All right, so along comes the this compression wave. It's going to go right through. It doesn't care whether the cardboard is oriented horizontally, or whether it's located vertically like that, or if instead, let's say that we made the slit be horizontal like that. Okay, this wave is it's a longitudinal wave, so it's going to come through exactly the same, regardless of which way the cardboard is oriented. That a longitudinal wave is not going to be affected when we turn the cardboard. Okay, so with that in mind, let's do a little experiment here. What you see right here is a piece of plastic that has a special kind of a coating on it. It's called a polarizing filter, and it's made by a company called Polaroid. You guys I don't know if you've ever heard of Polaroid. It was a really big company before. They made film and cameras and things. Well, they got their start in life by making polarizing filters. That's where they got the name from. So what they do is they take a bunch of long chain hydrocarbon polymer molecules, and they have a nifty way of making them so that all of the molecules are all oriented in the same direction. So imagine you've got a really long skinny molecule, and right next to it is another really long skinny molecule, and then another one. So you got gazillions of these long skinny molecules, and they're all oriented the same way. It behaves exactly like the cardboard with that slit cut in it. So what I do is I look at this and I try the rotation trick, and I see if that affects the light. All right, so let's come over here. So here is my desk lamp. Okay. So I'm going to take this polarizing filter. I'm going to hold it in front of the light, and I'm going to try rotating it to see what happens. Nothing. No effect whatsoever. So I'm thinking, I wonder if that means the light is a longitudinal wave. That's odd, because I remember my junior high school teacher told me the light was a transverse wave, but it certainly doesn't look like it. Well, let's take two of them. Okay, so two identical polarizing filters. So I'm going to put the first one in front of the light, and this one I'm going to hold still. I'm not going to rotate this one. The second one is the one I'm going to rotate. So I put it in front of the light, and I don't really notice anything happening. But now watch what happens when I rotate the second filter. You see that? The light goes away. When I rotate it back, the light comes back. When I rotate it like this, the light goes away. So light actually is a transverse wave, right? So why is it that we needed to have two filters in order for that to happen? Well, Here's the reason. All of the photons that are coming to us from that light bulb, each individual photon is definitely polarized, but there's gazillions of these photons and they're all completely independent from each other. So one of the photons might be vibrating in the horizontal direction, and another photon one horizontal, one vertical, and another one's off at an angle. So what's happening is when I put this polarizing filter in front of the light here, it's cutting out half of the photons, but the other half are getting through. So let's suppose that right now, all of the photons that just happen to have their polarization angle oriented horizontally, those are the ones that are being blocked. And the ones that have it oriented vertically, those are the ones that are getting through. Now, when I rotate it, the ones that used to get blocked are now getting through. And the ones that used to get through are now getting blocked. But the number that is getting through is the same here as it is here. So I don't notice a difference. In order to see a difference, that's why I need the second sheet. So right now, the only photons that are getting through are the ones whose polarization angle happens to be vertical. So if I take my second sheet and I hold it in the vertical direction, they all still get through. It's only when I rotate the second one like this that they no longer get through, because only the ones that are aligned vertically get through the first sheet. And so when I rotate this one the other way, he's now blocking all of those, right? So this experiment that you've just seen there, it shows that light is in fact a transverse wave. So now we understand a lot more about light than we used to. We now understand that light is not a continuous wave, it's a quantized wave, what we call a photon. And we understand that it's actually a transverse wave, not a longitudinal wave. Now, when you get into polarization, you see a lot of really interesting things happening. You guys know, of course, that if you look on Canvas, there are some extra credit opportunities. You guys, it's been a long time since anybody has turned in any extra credit opportunities. You guys really should. You know that term 3 is going to be ending in just a couple of weeks here. And some of you desperately need extra credit opportunities. The rules that I do for my extra credit opportunities are that you can only get extra credit if you talk about if you answer the question before we get to it in class. All right, so what you're seeing right now is the page in Canvas that this is extra credit opportunities, where these are videos that I have created, and these are all sailing related videos. So if you scroll down here, there's a bunch of these. So this is one that you can no longer get extra credit for because we've talked about it. This is one you can no longer get extra credit for because we talked about it, and so forth and so on. If we just scrolling down here, here's one that we haven't talked about yet. This is one that you could have gotten extra credit for if you had done this one prior to today, but it's now too late. You can no longer get extra credit for it. But let's watch it anyway. Okay, so let's watch it on YouTube. That way we can make it be, well, here we go. Okay, let's make it be full screen. Come on, what's the delay? Here we go. Notice all the glare on the ocean from the sun reflecting off the surface of the water. Okay, I'm going to hold up my sunglasses here. Notice how the glare is really substantially reduced. Watch what happens when I rotate my sunglasses 90 degrees. Ooh, all the glare is back. Okay, rotate them back to normal. Glare is gone, or at least dramatically reduced. Okay, one more time. Rotate them 90 degrees, there's all the glare. Rotate them back to normal, glare is gone. Okay, your job is to explain that. Okay, so if you had written up an explanation of that prior to today, I would have given you extra credit for it, but it's too late now. So let's go back and let's look some more at this. Let me bring this up. Okay, so what I'm going to do is I'm going to take my light and I'm going to turn it like this so that now you can see that we're getting reflection off of the polished wood here. Let's see what happens if I take my polarizing filter and I put it up here on the wood. Okay, so you can see that the reflection is still getting through, but when I rotate, or actually, okay, let's do it this way. Works better from this angle here. Okay, so look at the reflection, and you see how here the reflection is a lot less, and here you see the reflection more. Now it's not 100%, but there's definitely a difference. Here, the reflections are minimized. I mean, you still see a little bit of reflection, but not as much. Turn it like this, and the reflection, it comes back. Okay, so this is the same thing that's happening out on the ocean, is that when photons come in at an angle and they hit some surface, okay, some of the photons get absorbed or transmitted, and some of the photons get reflected. And it turns out that the amount of photons that gets reflected depends on what their polarization angle is. The photons that are polarized in one direction, they are more likely to get reflected, whereas photons that are polarized in the other direction, they are more likely to get absorbed or transmitted. And so this is why if you go out sailing, it's a good idea to have polarized sunglasses, because that way it cuts off the glare, because the glare off the ocean is at least partially polarized. Now, you'll notice the glasses didn't completely cut down all of the reflected light. You know, they didn't get rid of all of it, they just cut down on it. Okay, so the light that's reflected off the ocean isn't 100% polarized, but a lot of it is. So by wearing polarized sunglasses, you can cut down on the glare, while you can still see the other things. Like if there's a swimmer in the water, the light that's reflecting off the swimmer's head is not going to be polarized, but the glare that's reflecting off the water around the swimmer is going to be polarized. So when you put on the polarizing sunglasses, you can see the swimmer in the water a lot better. Now, while we're at it, let's take a look at something else. You guys know that behind me, I always have my computer monitor with some sort of a soothing image on it. Let's play around with that. Let's see what happens there. Okay, so I'm going to hold the thing up here, and what you see is total blackness. No light is getting through. But when I rotate it like this, now all of a sudden the light is getting through. Turn it like this, it goes black. Turn it like this, it gets through. Oh, that's interesting. I wonder why that's going on like that. Well, guess what? There is a extra credit opportunity here that, okay, if you go back into Canvas again and look at the extra credit opportunities, here I have the videos that are created by students. We call it Physics of Everyday Life. If you scroll down here, you'll see a bunch of videos here. And in fact, this very first video is very much like the one that I just talked about here. So in fact, let's take a second and let's play this video real quick. And let me make it be full screen.
Oh, hi, Brittany. What are you doing?
Oh, hi, Angelica. I just came outside for a while to catch some sunshine and to read a book on my Kindle, but my Kindle isn't working. I turned it on, but the screen's black.
Why do you say that? The screen's not black. Look at it. It's working just fine.
No, it's not. The screen is totally black. You look at it.
Try taking off your sunglasses.
I don't see what difference that'll make, but okay. Hey, you're right. The screen isn't black after all. Why couldn't I see anything on it before, but I can now?
It's probably because of your sunglasses.
Why would sunglasses make it so I can't see what's on the Kindle screen? And wait a second, you're wearing sunglasses too. Why could you see through your sunglasses, but I can't through mine?
It probably has to do with physics. You know what? I bet Mr. Hendricks would give extra credit to someone who can answer those questions.
She's right. Mr. Hendricks will give extra credit to someone who can answer that question. Okay, so clearly the one girl's glasses are polarized and the other girl is wearing non-polarized glasses. Okay, but that isn't what I'm looking for. If you want to get extra credit, This one, I will allow you to do this one, but you've got to do it before we meet next time. If you can go through and explain why it is that I can take a Kindle, or maybe I can take a flat screen TV, and if you can explain why it is that I see light now and I don't see light then, okay, then I will give you extra credit. But I will not allow you to say, well, obviously the TV screen is polarized, right? That's not good enough. I need you to explain, how does a flat screen TV work? And why is polarization the key to understanding how it works? Now, I do need to warn you that not all TVs are going to do this. There are some kinds of TVs that are called LCD TVs, liquid crystal displays, and there are other types of flat screen TVs that are called plasma screens. So if you do this with the plasma screen, you're not going to see the effect. It's only going to be an LCD screen that you're going to see it. So if you can do some research and to figure out, how does an LCD screen work? And why is polarization the key to how it works? If you do that and write it up and submit it before we meet next time, I'll give you a little bit of extra credit. But if you wait until after next time, then I'm going to say, hey, it's too late, no more. Okay, so hopefully we understand a lot more about light now. Now there's one other thing about light that I've talked about, but I haven't explained why it does it. And so let's go back into, let's do a little review here. Hopefully you guys remember that one of the reasons why scientists were convinced the light could not be a wave was because when they looked at the shadows, they saw sharp edges on the shadows. And they said, but that's not what waves do, because they were familiar with waves like this. And they know how much diffraction they should expect from a wave. And so even though the edges of the shadow are a little bit fuzzy, they said, no, that's not good enough, because if light really is a wave, it should diffract. And they kind of estimated how much it should diffract. And they said it should diffract so much that these edges should not be even close to sharp at all. It should be totally, totally fuzzy. So the reason that we explain for why that's understandable is because light has a much smaller wavelength than the people ever imagined that it would. I mean, they assumed that if light was a wave, it would have a wavelength that's similar to the kinds of waves that they're familiar with, sound waves and water waves. And so if light did in fact have a wavelength that was that long, it would diffract so much that you would not see sharp edges at all. Okay, but in fact, light does not have a wavelength that long. Light has a super, super short wavelength. It's so short that it's actually measured in nanometers, which is billions of meters. So what I told you last time, without explaining the reason why, is that I told you that light diffracts a lot when the wavelength is long. It does not diffract as much when the wavelength is short. So I just told you that, but I didn't explain why it did that. Well, today we're going to learn why it does that. And the key is something called Huygens Principle. So there's a scientist whose name was Huygens. He was a Dutch scientist. So let me, okay. If you were to go into your homework tonight, so this is the page on Canvas that tells you what your homework is going to be tonight. Here is a video that describes this thing called Huygens Principle. And rather than me explaining it to you, I think it's better to just, let's watch a few minutes from this video and let's see how it explains it, because they do a lot of really good animations that are much better quality than I could ever hope to do. All right, so let's take a minute and watch this short little video on Huygens Principle. Okay, here goes.
This lecture is about diffraction and Huygens Principle. Huygens Principle states that every point of an advancing wavefront is a new center of disturbance from which emanate independent waves in all directions. This can be a little strange, but I think it'll start to make sense if I give you a kind of visual example. So first of all, what does this principle mean by a center of disturbance? Well, a center of disturbance is a kind of center from which disturbances are radiating outward in all directions. An example would be if you throw a stone into a pond, the place where the stone enters the water is a center of disturbance, and waves spread out in all directions from that one point of disturbance. So as an example, if this red dot is a center of disturbance, waves are going to radiate out in all directions like this. So Huygens' principle says that every point of an advancing wavefront is a new center of disturbance from which emanate independent waves in all directions. So what that means is that if we choose any one point on this advancing wave, it behaves like a center of disturbance. So I chose that point in the middle, and we can have a new wave radiating out in all directions. I've given this new wave the same wavelength as all the other waves in this wavefront, so you can see it has that same wavelength. So this is a little strange because if we're imagining this wavefront moving forward, there's no reason why it would suddenly radiate into a circle. And the reason why it's not doing that is that that one point is just one point on the wavefront. And what Huygens' principle is saying is that every single point along that line is behaving like a new center of disturbance. So I could put more points here and draw the waves radiating off of them because they are centers of disturbances, and I could add more and more. And you can start to see a pattern where there's one very specific spot where all of these waves are overlapping, and that's going to be right here. So that's where the next wavefront occurs. So what Huygens' principle is saying basically is that if you take every single point in a kind of straight line wave and model it as a center of disturbance, the waves radiating from all those centers of disturbance perfectly cancel out to make the shape of the wave that you're trying to predict. So here that's just going to be another straight line. That's where the next wavefront will occur. So why do we care about this idea? Well, this can help us predict how waves will interact when they hit barriers. When waves of light pass through a small opening in a barrier and as a result radiate out in all directions on the other side, we call this diffraction. This is a result of Huygens' principle. Every part of the wavefront would spread out in all directions, but most of the wavefront is blocked by the material, so the part that can spread out is not interfered with as it spreads. So we can imagine this wavefront approaching the solid barrier. And when it hits the solid barrier, most of the wave is not able to move through the barrier. The only part that is going to be able to is this small point in the center. And I know that every single point along that line is behaving like a center of disturbance. So that means that on the other side of this barrier, the wave is going to radiate out in all directions like this. So this is how the wave is going to behave when it moves through a very small opening. It's going to change from all moving together as one kind of solid front to spreading out in all directions like this. So this is what happens during diffraction, when a wave of light passes through a small opening in a barrier and as a result radiates outward in all directions on the other side. We can use Huygens' principle to predict the diffraction pattern for different shapes of barriers. To use Huygens' principle to predict diffraction patterns, we're going to start by drawing points on the wavefront only where it is not making contact with the barrier. Each point will be a center of disturbance. These points can only propagate when they're not up against a barrier. So I'm only going to draw points where there is no barrier. Next, draw circles around each center of disturbance. The circle's radius should be exactly one wavelength. So if I draw those circles, this is what that looks like. Next, we're going to draw a new wavefront along the line where the circles meet in constructive interference. So that's going to look like this. That's where all the circles are meeting together in constructive interference and not being canceled out by other waves. So this is what the new line of the wavefront will look like as it moves through the barrier. This kind of makes sense. If we imagine water impacting a barrier, we would imagine on the other side the water would kind of begin to spread out back toward the center like this. We can then repeat this process to find the next wavefront. If I were to draw more dots along those lines and draw circles around them, this is what the next wavefront would look like.
Okay, so I'm going to stop it there because there's one point that he didn't make that I want to make. So hopefully now you understand how Huygens' principle can help you predict how the wave is going to propagate. And so let's draw two pictures here. One picture is we have a wave going through a very small opening. All right. And so along comes the wave. So here's the wave front, wave comes over here. So each one of these points along the wave front is the center of a new disturbance. And so when I combine them all together, it combines together to be a straight line like that. But if all of these guys are all blocked and all these guys are blocked, so the only thing that can get through is right here, then when it comes out the other side, because this point right here doesn't have the neighbors. See over here, back here, this guy, he had lots of neighbors on either side. Up above him and down below him, he's got lots of neighbors. And so when his wave combines with all of his neighbors' wave, it combines together in a way that gives a what we call a plane wave. But now he comes through the opening. His neighbors are no longer there. So his wave is going to do what his wave would always do. It comes out as a circle. And because he doesn't have any neighbors to interfere with, then it's just going to travel out like that. So you're going to get a lot of diffraction. Now, what if you have the same situation, but this time it's a really big opening? All right, so along come our waves. So here's the waves coming along, and each one acts as a point, and all of the points together, they add up to give you a new one. And again, each one adds up. And because every point here has lots of neighbors on this side and lots of neighbors on that side, it adds up to be a plane wave. And so the thing just propagates forward like that. Okay, so now the wave gets to this point right here. So everybody up here is blocked. Everybody in here is blocked. Let's look at this guy in the middle. This guy in the middle is going to do what Huygens Principle says he's going to do. He's going to spread out like this. And he's got lots of neighbors on this side that are all doing the same thing. And he's got lots of neighbors on this side that are all doing the same thing. So when you combine them together, what you get is a nice wavefront like that. And it's going to continue on through. So anybody who is far away from these edges, they are going to continue on forward as if there was no barrier at all. But what about this guy over here? This guy, he has neighbors on the one side, but all of his neighbors on the other side, they all got blocked. So he's going to do what Huygens Principle says he's going to do, and he's going to go like that. Okay, but he's just one guy. And down here, we've got hundreds or maybe thousands or maybe millions of other guys that are all going straight through. And you only got like one or two guys on the edge here that are being diffracted. So if you got millions of photons that are all going straight through, and you've only got a few photons over here that are going off at an angle, well, these are the ones you're going to see. Your eye is going to notice all of the millions of photons here. And your eye is not going to be sensitive enough to notice that there are a few of them being over here that are being diffracted, but these guys are far outnumbered by the ones that are going straight through. Whereas over on the left side here, you've only got this one guy, and he doesn't have neighbors, and so they're not canceling them out. So hopefully you see that Huygens Principle explains why it is that when a wave goes through an opening that is small compared to the wavelength, you get lots of diffraction. But when that wave goes through an opening that's large compared to the wavelength, then you don't have as much noticeable diffraction. I mean, there's always going to be a little bit, but most of the wave goes right straight through. And so you could easily get fooled into thinking that there's no diffraction, even though there actually is. Huygens Principle is the thing that describes all this. Okay, so I'm hoping that makes sense to you. Yes? All right, so I think we're in a good position to do the homework now. Let's go back to...
And then this one would be the one after that.
No,
so the wave kind of returns to...
I don't want you anymore. All right, let's go back to here. All right, so here is the homework for tonight. Now I do have a couple problems out of the book, but I'm only giving you 4 problems out of the book. And then I have these 3 questions that I want you to answer. What I want you to do is I want you to write a few sentences that describe how it is that Huygens Principle explains why it is that waves diffract more when the wavelength is big compared to the opening than they do when the wavelength is small compared to the opening. So explain, or write up telling how it is that Huygens principle explains that. And then the other one here is to explain how does Huygens principle explain why refraction occurs. So maybe, yeah, we should definitely talk and stop and let's talk about that for a minute. This is something that probably we'd better explain. Okay, so refraction, hopefully you guys remember, is this. We talked about this before, but only briefly. What if you've got something like, let's suppose that this is a light ray, and let's suppose that this is air, and then this is the interface where it hits the water. So we, back almost a month ago, we talked about the fact that if light comes in at an angle like this, some of the light gets reflected, but some of the light gets transmitted. But the important thing is that the transmitted light is not in the same line as the incoming light was. The direction changes. So this change in direction here, this is called refraction. Huygens principle explains why refraction occurs. If you imagine Huygens principle, so along here, we've got all these dots here, and each one of these dots is the source of a new wavefront. And because every dot has lots of neighbors on each side, the new wavefront is right here. And then when we do the same thing again, we get a new wavefront right here. We do the same thing again. But now when we get down here, this is interesting. This guy right here, he is the source of a new wavefront, but he is in water. And the speed of the wave is slower in water. And that means that this guy does not travel as far as his neighbors up here. These guys, they traveled the same distance that they did before. But this guy, the new wave is traveling more slowly. And so when we do Huygens principle, what we're going to get is we're going to get a wavefront that's like this. It's got a kink in it. And then over here, we get another kink in it right here. And right here, we get another kink right there. Because each one of these guys is doing what Huygens principle says he needs to do. But the wavelength is smaller here. Okay, so it's smaller on this side. And the wavelength is larger in this side, right? And so what you get is these weird shaped wavefronts that are kinked like that. And then once the full wave hits here, it goes like that. And so you can see that the direction of the wave, which is always perpendicular to the wave fronts, the direction of the wave has changed. And so the light, which used to be traveling this direction, is now traveling this direction. Huygens principle explains all of that. Okay, so for your homework tonight, I want you to write up an explanation of those two things. And then I also want you to write up a few sentences explaining why it is that thin film interference only occurs when the film is indeed thin. If the thickness exceeds the coherence length of the photon, then the part of the photon that reflected off the front surface is not going to be able to interfere with the part of that same photon that reflected off of the rear surface, because the shift there is greater than the coherence length of the photon. So if the film gets to be too thick, and when I say too thick, I mean more than just a couple wavelengths thick, then you're not going to get interference anymore. Thin film interference only occurs when the film is indeed thin. That's why we call it thin film interference. Okay, so I want you just to write up a couple sentences explaining that. And then I want you to go ahead and open up the book and do these problems right here from chapter 16. Now, I strongly recommend that you watch this video a second time. I think this video is a very well done video. And we didn't watch the entire thing. We only watched part of it. I'd recommend you go back and watch the thing a second time. Okay, so I realize I hit you with a whole lot of information today. I hope that I didn't overwhelm you. Remember, everything we're doing today is being recorded. So if you go back tonight, if you look at Canvas tonight, I'll have this recording posted on Canvas. You can watch it again. So if you don't have any questions, you can go ahead and type "bye" in the chat box, and I'll see you later. If you do have questions, then here, let me turn off the recording so that we can talk without the embarrassment of knowing that you're being recorded.